We are Team 19, comprised of Evan, Sandra, Remy, Pablo, and myself. Next. So for contents of proposal, below it's shown is the 3D printer that we chose. The production volume is estimated around 300,000 units annually in 2023, most of the production coming from the United States. The industry is expected to grow by about 20% compound annual growth rate. Our primary and secondary customers are product designers for prototyping. Secondary customers are medical professionals for prosthesis, implants, and hobbyists as well for custom art and other items. Next. So here is our CAD modules from our before and after for our primary and secondary. Next. Again, so primary and secondary users, we have listed engineers and product designers, medical professionals, hobbyists, research R&D department, and small and medium enterprises are for prosthetics and implants again. So next.
Going on to our product analysis. In order to meet our primary function of printing the design, we've developed a function analysis to show all of our functional criteria. The function component mapping matrix shows the main functions of each of our primary components. In the quad chart, the LCD, frame, stepper motors, extruder, and control board are both important and have a high cost, which indicates a need for redesign in order to decrease costs. Going on to our product family design. The functional designs are very similar, but the designs between primary and secondary consumers differ in terms of temperature regulation and precision control. Our design has modules for the cooling fan and extruder assembly, which makes it much easier to assemble the different designs within the family. Here are the CAD drawings for the modules. So our main module variant is the addition of this second spool to hold a filament of a different color or material. And then here's the CAD drawing for the common interfaces. Our common interface between the variants is the bar they rotate around. This remains the same between designs, and either one or two spools can be added. For our assembly sequence, in order to decrease the number of nodes, we can use the modularity of the printer to our advantage by adding the extruder, cooling fans, and filament spools at the end of the assembly sequence. We are able to simplify our process, keeping a standard printer until the addition of the primary and secondary variations.
Moving on, design for assembly. This slide focuses on improving the efficiency of manual assembly for a 3D printer. It identifies high-impact areas such as the LCD housing assembly and the stepper motor mount, which take the most time due to factors like screw fastening and complex wiring. We have picked up stepper motors for designing parts and consolidating function. Even it is a purchased part, it requires several screws to be installed. Also, it aligns with the quad chart characterization for being redesigned. Next. Stepper motor has the function of melt filament and feed filament, an LCD of hold components. Next. The stepper motor mount redesign applies several DfM principles for improving the efficiency by reducing fastener from 8 to 4 screws, adding locating features for better alignment, increasing part symmetry, and consolidating parts into a single piece. We streamline the assembly process. These changes did not affect the product functionality, but reduced manufacturing costs. Additionally, assembly time was cut off from 85 seconds to 35 seconds, significantly improving the efficiency. Next. The original design, as we could see here in the 3D CAD, used 4 screws for each stepper motor. Now with the new design, optimize this by reducing it to 2 screws, which minimize complexity and assembly time. 2 locating features such as chamfers or alignment guides are incorporated to ensure precise positioning of the motor during the installation, eliminating any alignment issues. Next.
Moving on to design for automated assembly, we analyzed the LCD screen assembly because it has a high assembly cost, high functional importance, and it's a small and lightweight assembly with three main components. We took the four DFA steps to simplify the assembly process. We reduced its fasteners, preferred some snap fits, increased part symmetry, and provided locating features. These changes provided no functional difference, but significantly reduced the total assembly cost from 28 cents to 12 cents, which is about a 56% reduction. You could see the difference in the design before and after, increasing the part symmetry by adding the hole on the other side, getting rid of the long screw holes through the part and adding instead locating features, and then adding small holes on the sides of the part for the snap fits to snap into. And looking at the spreadsheet below, you can see how I calculated the percent change in assembly costs.
Going now into our process selection. For the frame, we decided on aluminum for the material because it's both lightweight and can support the weight of other components. The critical dimensions here are length, width, and height, as the frame must hold all the other components inside of it. The tolerance is set at 0.1 millimeters to ensure a correct fit with all the other parts. Out of the processes compatible with aluminum on the shape, the only two that pass are sheet metal working and machining. And given the shape and the need to be bent, we decided to use sheet metal working here. For the LCD case, we decided to use a thermoplastic since it is lightweight but sturdy enough to protect components of the LCD screen. Critical dimensions here are length and depth as indicated on the drawing, and the tolerance is set at 0.02 millimeters so we can make sure the LCD screen will attach to the casing without issue. Most of the processes compatible with thermoplastics fail due to the non-circular prismatic shape. We selected injection molding over machining for the cost benefits and the need for less material in production.
In the LCD casing before DfM, we see that the total cost of manufacturing is $1.07, and that DfM Pro has 8 instances of recommendations for changes. Then after the redesign, we see the total cost has moved down to 80 cents, and the recommendations given by DfM Pro are significantly less. Once again, we achieve symmetry by removing the back panel and remove the screw holes for the top surface, and then added locating features instead, significantly decreasing both the manufacturing and assembly cost.
Here you can see the DFM for the frame. The before cost was $10.62, and we only had one instance of recommended by DFM Pro. Clearly after, we have reduced our cost by almost over half, but down to $4.73, and that was by reducing sheet thickness and removing the side angle cuts at the sheet corners. As you can see, again, DfM Pro is still only recommending one.
Moving on to the product service system design, we have made sure that the diagnostics is done at the through level, which warrants the replacement of each through versus ordering the new printer. We also made the upgrades modular to make sure that we also extend the life of the existing machines. In terms of the recurring service revenue, we made sure that we create contracts for printing plastics, and we also made printing shareable by using paper print model, stimulating the use of shared printers at the academia customers. This ensures that we maximize the value of our 3D printers to our customers over an extended period of time. Lastly, in conclusion, we have achieved a saving through DFA and DFM, and we have also we have a few critic points. One is we would require further redesign of extruder assembly to optimize assembly times, and additional DFM is required for rails and certain other components to further optimize